Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing series inverter and parallel inverter. And here, let us firstly discuss series inverter. What is series inverter? And basically, in these particular series inverter and parallel inverter, here we are making use of thyristors. And so far, the inverters which we have discussed, we were only making use of transistors or otherwise GTO, MOSFET, IGBT. And here in series inverter as well as in parallel inverter especially, we'll be discussing making use of thyristors over here. And here, if at all, if the commutating components, why commutating components? What is commutating component? Whenever we will have to commutate the devices which we are actually using of in any particular circuit. In that case, those components, we call it as commutating components. And here, the commutating components are inductor as well as capacitor. And whenever these commutating components like inductor and capacitor, whenever it is connected in series with the load, we call it as series inverter. And here, firstly, if you see here, we are making use of an inductor and capacitor which is connected in series with the load, that is R, resistive load. And initially, here the capacitor will be charged to the negative voltage, and initially at this instant called T1, here we are actually providing the triggering pulse for the transistor 1. And when triggering pulse is actually provided for the transistor 1, in that case, the individual circuit diagram is T1. Current flows through. When triggering pulse is provided, at that instant only thyristor gets turned on and it starts conducting current through the load in this direction through inductor, capacitor, resistor and back to supply. And current flow through the load is in this direction. So, capacitor is initially charged to the negative voltage, and when triggering pulse is provided for the thyristor, it is conducting a current through the load in this direction. And the moment when the capacitor voltage is reached VDC, at that instant, the current flow through the load will be maximum. And if you see here, the current is actually sinusoidal. Why is that so? Why is the current flow through the load is sinusoidal? It is because we are making use of a series RLC circuit, and that is the only reason current flow through the load is sinusoidal, is increasing in the sinusoidal direction. And the moment the capacitor voltage reaches VDC, at that instant output current through the load becomes maximum. And later the current flow through the load is getting reduced and it is almost becoming zero by the time the voltage is charged to positive voltage, and this particular capacitor holds this particular charge, positive charge, and by that time the transistor the current through the load is finally zero. And now at this instant called T3, here we are providing the triggering pulse for the thyristor 2. And if you see, this is the thyristor 2, and because of the connection of the thyristor 2, the current flow through the load will be in the reverse direction to that of the first case. If you see, current flow through the load was from, let us say this point is A and this point is B. Current flow through the load is in downwards direction, that is from A to B. Whereas here, because of when we are providing the triggering pulse for the thyristor 2, it is conducting current flow in the reverse direction to that of the first case. From B to A, current is flowing in the upwards direction, which is exactly reverse to that of the first case. So that is the only reason here current flow through the load is in the negative direction. And now the moment it reaches maximum, the current is becoming zero. Current through the charge through the capacitor is becoming zero, and later this particular current through the load is finally becoming zero at this instant called T4, and by that time the capacitor is completely negative. The charge across the capacitor is now negative, and by that time the thyristor is the current through the load is becoming 0. And this is the voltage across the load, and this is the current across the load. This is nothing but output voltage, and here output voltage will be just similar to that of the output current, because we are making use of resistive load. Here output current as well as output voltage are nearly same, but there are certain disadvantages associated with these particular series inverters. So here maximum frequency of inverter is limited to ringing frequency of RLC circuit. So that is the thing. Here frequency of the inverter is limited. That is the thing. And the other thing is load current flows through commutating components like inductance as well as capacitance, and they must have high current rating, because these particular inductor as well as capacitor is also carrying the load current along with the load. These particular inductor as well as capacitor need to possess high current rating. So that is one of the limitations. And the other thing is energy is taken from the source in one of the half cycle. Hence, peak current requirement is more. Energy is directly taken from the source in one of the half cycle. Hence, peak current requirement is more. And there is distortion in output current as well as output voltage waveform. If you conduct the experiment of series inverter also, you may observe in the lab, the output waveform will be fully distorted. That is a disadvantage associated with a series inverter. So, in order to overcome all these disadvantages associated with series inverters, we are actually moving on to the parallel inverter. So here in parallel inverter, a capacitor is connected in parallel with the primary of the transformer, and if you see the commutating component is nothing but capacitance over here, and since this commutating component is connected in parallel with the primary of the transformer, we call it as parallel inverter. And if you observe, the load is connected across the secondary of the transformer. Load is connected across the secondary of the transformer. So, initially, this capacitor will be charged to a voltage of opposite polarity as that it is shown in the circuit diagram. So, here it will be charged to minus VDC initially. Capacitor will be charged to minus VDC initially to the negative voltage, such that because of the transformer action, see, it is only half of the primary, across half of the primary minus VDC is applied. That means due to the auto transformer action, the voltage across this particular complete primary will be 2 VDC. Yes, with the polarity negative and positive. And it is actually charged in the negative direction. Capacitor is actually charged in the negative direction initially. And the moment when we provide the triggering pulse for the thyristor 1, that is IGT1, when we have provided the triggering pulse, at that instant, the thyristor started conducting current through the load. Thyristor started conducting current through the load in this direction. So what? Current starts flowing, and that is how the output voltage started appearing across the load. And the moment it reaches this instant, we are actually providing the triggering pulse for the thyristor 2. That is IGT2 triggering pulse we have provided for the transistor 2 now. Previously transistor 1 conducted, and now we are providing the triggering pulse for the transistor 2 at that instant. Here, now, whatever the negative voltage will be appeared across the thyristor 1, such that particular thyristor 1 will be getting turned off because of this 2 VDC which is applied across the anode of the thyristor 1. That is how thyristor 1 gets automatically turned off, and that is the only reason why we are making use of a commutating component, so-called capacitor over here. Because minus 2 VDC will be appeared across the anode of the thyristor 1. That is how it gets turned off now, and current will be flowing through the T2 alone. So here T2 is conducting a current through the load. T2 is conducting current through the load in this direction. So that is how the parallel inverter. And here if you see the output voltage of parallel inverter is a square waveform, which is much better when compared to that of a series inverter. That is one of the advantages which is associated with the parallel inverter. And the other is here simple commutation circuit. The commutation circuit is simple. The thyristors are easily turned off, and here switching frequency is also high when compared to that of series inverter. Their frequency, it depends upon the commutating components like resistor, inductor as well as capacitor, whereas here when compared, switching frequency is higher. So these are the advantages associated with parallel inverter over series inverter. And here coming to the disadvantage part, the disadvantage is large amount of energy will be trapped in this particular capacitor, which we are actually making use as a commutating component. And this energy, whatever the trapped energy, it need to be removed with the help of additional feedback diodes. So we will have to invest in the additional equipment in addition to that of the already existing equipment, which increases the investment cost. So that is the disadvantage associated with this particular parallel inverter. Or otherwise, heavy transformer is required in order to carry the load current. That is another investment which is actually included for the parallel inverter. So these are the disadvantages associated. And in the coming up lecture, we'll be seeing problems. Thank you.